Okay, so this video is going to show you how to do critical values for goodness of fit, chi-square for two-way tables or contingency tables, and a quick example for finding a critical value for a NOVA, single way or one-way in NOVA. So here's some data, and I pulled this right off one of the homeworks. When you look at this, I have a set of categories. I have a set of observations with this. So we're testing goodness of fit and equal outcomes. So I'm just going to go in and do that test really fast. So stat, goodness of fit, chi-square, observations are in, number in package, and equal proportion. And hit compute. Now I'm doing the test for a particular reason, and that particular reason is right there. That 5 is the degrees of freedom. Now for good chi-square goodness of fit, that should be fairly intuitive because you have 6 different categories. 6 minus 1 would give you 5 degrees of freedom. Now the reason I need to look that up is when I go to look up the critical value, stat, calculator, I have chi-square. Bring up the chi-square, I put in my degrees of freedom is 5, and depending on what the significance level is, so if the significance level is 5%, then I would keep this pointing this way, x less than some number, this is what we want. I'm not going to put in 5%, I'm going to put in 0.95 for 95%. The 5% would be in the upper end. Hit compute. So my critical value would be 11.07. Notice my test stat's bigger than that, so I would reject. That's equivalent to the p-value being less than the alpha. If I wind this up to 0.99, my number should be bigger. If I wind it down to 0.90, be smaller. This will be an alpha of 10%. Now, reduce this, get rid of that. Here's the next one. This is another data table from your homework, and I notice I have 2 categories of numbers, 2 categories of numbers. That's a chi-square for two-way tables. Categories, categories. So when I do that one, stat, tables, contingency, summary, and make sure I don't screw up here, and that would be man and woman for the select columns. The row labels would be in the one before it. And I'm going to click these because it's always a good habit to have both of these clicked. I'm just hitting compute. And what I'm really after here is that right there, degrees of freedom. But now, where's it coming from? Well, you notice there's 2 rows, or excuse me, 2 columns and 2 rows. So if I look at the degrees of freedom for the columns, it'd be 2 minus 1 or 1. If I look for the rows, it's 2 rows, so 2 minus 1 is 1. And I would take the degrees of freedom for the rows times the degrees of freedom for the columns, so 1 times 1 is 1. So to look up, we'd reject here by the way, we would look up the critical value by again going to calculators, still chi-square, degrees of freedom is 1, get rid of this, and then whatever 100 minus your alpha is. So if alpha is 1%, I put in 0.99. That would be my cutoff. That would be my critical value. If alpha was 10%, I'd put in 0.9. And you can see the area I have shaded is the non-rejection region. The area is not shaded as rejection. So that's probably about the easiest way to do those. If I next want to do an ANOVA, so here I have 4 treatments. No treatment, fertilizer on some crop, irrigation on some crop, fertilizer and irrigation on a crop. So I'm looking for a mean of whatever they're measuring with these different treatments, but this is ANOVA one way. And make sure I get all of them here. No treatment, fertilizer, and irrigation. Check my Tukey again for habit. Hit compute. And I would definitely reject here. And you can look at the Tukey results if you want. I'll let you pause it if you want to go through them, but it looks to me like no treatment and fertilizer and irrigation are looking pretty much the same, and fertilizer and irrigation is different. And if we went up and look at the mean, I'm seeing the mean's much larger, so that would kind of make sense that they're measuring either yield or growth. But again, what I'm interested in is these columns here, degrees of freedom. And when I have the degrees of freedom, we have columns, air, and total. Okay, now I haven't talked about this yet in class, but to get this F stat, I'm taking this column here, these two values under MS. MS stands for mean square. Actually, it's just the variance of the values in the columns. This is the variance of the error. And if I take this value divided by that value, you will get that F stat. So this is in the numerator, that's in the denominator. When I look at degrees of freedom, I have 3 degrees of freedom in the numerator, 16 degrees of freedom in the denominator. I'm going to move this over here in hopes that I can still see it. Stat, calculator. This is an F. ANOVA is an F. Numerator degrees of freedom. That would give me a 3. Denominator degrees of freedom. That would give me a 16. And again, clear this. Alpha. Well, if alpha is 5%, I'd have 0.95. So this would be where I would reject. This is more like the acceptance region, non-rejection region. I don't like saying the acceptance region, but you know. But my critical value would be 3.238. And if I look at that test stat right there, I'm way over that. That's equivalent to my p-value being under my alpha level. So again, run the tests, chi-square goodness of fit, chi-square for contingency tables, one-way ANOVA, whatever. Get your degrees of freedom, and then you can look up the critical value for these My Math Lab assignments. All right?